The nature of magnetism. Magnets were first discovered over 2,000 years ago by the Chinese and the Greeks and were used for various non-scientific purposes. The name was coined by the Greeks as certain magnetic rocks, like magnetite, were found in the province of Magnesia. Unlike electrical effects due to the rubbing of various substances, like amber, to separate the electrical charges so there would be attractive and repulsive forces, these magnets came out of the ground already attracting and repelling certain materials. It wasn't until after 1000 AD that Chinese, European, and Persian mariners separately used magnets for navigation. When a magnetic material was shaped in the form of a needle and floated on the surface of water, it always pointed in the same direction, towards the North Pole. Always being able to tell which direction was north was a critical factor in ushering in the age of exploration. It wasn't until 1600 when this phenomenon was explained by William Gilbert. But first, we will discuss the nature of magnetism. Magnets have two ends, also called poles, called north and south. Like poles repel, unlike poles attract. So you can see a south pole will attract a north pole, and a south pole will repel a south pole. A north pole will also repel a north pole. This attraction or repulsion is the magnetic force. When a magnet is cut in half, each piece still has a north and a south pole. No matter how many times the magnet is cut, the pieces still have a north and south pole. This works all the way down to the atomic level. We will investigate this more further on. Once again, there is no such thing as a north magnet or a south magnet. The poles cannot be isolated. Every magnet has both poles. The behavior of magnetic poles, north and south, are similar to electric charges, positive and negative, where opposite poles or charges attract and like poles or charges repel. There are two significant differences between these effects. One, certain materials are naturally magnetic, where electrical properties result from physical rubbing. And secondly, there are independent positive and negative charges, but magnetic materials always contain a north and a south pole. Electric field lines were used to show how electric charges would exert forces on other charges. A similar concept is used in magnetism. What's nice about magnetic field lines is that they're more easily seen. The above is a picture of iron filings sprinkled on a paper that's laying on top of a bar magnet. The iron filings all act like little bar magnets and align with the magnetic field of the large magnet. The field exits one end of the magnet and returns to the other end. Note also that the field lines extend through the magnet, making a complete loop, unlike electric field lines. So a line might start here, go all the way around into the magnet through, like that, a complete loop. Arbitrarily, magnetic field lines are defined as leaving the north pole of the magnet and re-entering at the south pole as shown. The lines specify the direction that the north pole of another magnet in the field will want to point towards. So if you put a little iron filing right here, like a little tiny bar magnet, the north pole would be this way and the south pole would be this way. So these arrows here show you the alignment. If you put a little iron filing here, it would align itself like this with the north pole and the south pole. If you put a little iron filing here, it would align itself with this field line, north and south. The more lines per unit area, the stronger the field. So here you can see that there's going to be a lot of magnetic force here and less here because you can see the density of lines is a lot greater here. The lines that seem to not be in loops are. We just ran out of room on the slide. So for example, this line here is going to go all the way around and back into the magnet. All magnetic field lines form complete loops and go right through the magnet. Like electric fields, different configurations of magnets will produce interesting magnetic fields. Two magnets with their north poles next to each other. Here, these two magnets are repelling each other, and you can see that there's no magnetic field in the middle because they cancel out. The fields cancel out right in the center. But you can see they create a very similar magnetic field to when you have two positive charges, right? Very similar configuration. And here we have two magnets with their opposite poles next to each other. So these magnets attract each other, and you can see that there's a line going directly from this north pole to that south pole. So there's nowhere in here where the magnetic field cancels out. You have a magnetic field right in the center here. The Earth's magnetic field is similar to that of a bar magnet. It is caused by the circulation of molten iron alloys in the Earth's outer core. More on this later. The Earth's north pole is really a south magnetic pole, as the north ends of other magnets are attracted to it. The magnetic poles are not located exactly along the Earth's axis of rotation, but they're close. They're a little bit off. The Earth's magnetic field extends from the core to the outer limits of the atmosphere, also known as the magnetosphere. The picture here, which is not to scale, shows the interaction of the solar wind with the Earth's magnetosphere. The solar wind has electrons, protons, alpha particles, heavy ions, and atomic nuclei. The magnetosphere protects life on Earth from being subjected to ionizing radiation that would otherwise cause great harm. Many of the particles in the solar wind are prevented from entering the Earth's atmosphere by the magnetosphere. Some particles enter the magnetosphere and are directed along the magnetic field lines to the magnetic north and south poles, where the fields are the strongest. Passing through the atmosphere, they collide with oxygen and nitrogen molecules, transferring their energy to excite the molecules, which then re-emit the energy in the form of light. This kinetic energy to light energy transformation produces the aurora borealis and aurora australis. The aurora borealis is shown from space here, encircling the south magnetic pole, which is the geographic North Pole.